Hi everyone, today we are going to have a look at resisted projectile motion. So apart from gravity, we're also going to look at how air resistance affect the motion of object being projected through the air. Okay, so before we go into it, let's have a quick recap on regular projectile motion with no air resistance. So horizontal components. Obviously, there's no horizontal acceleration. There is the object is not powered in any way, so it will just go. It will not undergo any acceleration in the horizontal axis. For the horizontal velocity is going to be consistent. It's just going to be the initial horizontal velocity throughout the entire trajectory. And then for the horizontal component, sorry, the horizontal displacement, it's just going to be the horizontal velocity times the time. So that's give you a displacement. I've included a initial horizontal displacement here to keep it as general as possible, but 99% of the time, this is just going to be zero. So you will not actually have a initial horizontal displacement. So you just start from origin. Sorry, it's this part equals to zero. So um, this is the horizontal part. In terms of vertical components, obviously there's always a vertical acceleration downwards due to gravity. And if you integrate it, you have this expression, which is basically the initial velocity minus the acceleration due to gravity over time. So uh, as time goes down, more and more velocity is lost in this part. Uh, so your total vertical velocity gets smaller and smaller until it goes into the negatives. That's when it's coming down. For vertical displacement, we integrate it again. So we have this expression. Obviously, once again, I introduced a initial vertical displacement. A lot of time, initial vertical displacement is not a zero. Okay, so it cannot be just assumed to be zero because a lot of times you will actually end up things like things being fired off a ledge or something, and you do have initial vertical displacement. Okay, to Cartesian equations. So if because both equations are in terms of a parameter t, then we can just reshuffle it and combine them into a single equation. So we express t in terms of x, and then we punch it into the equation, and we end up with this expression here. So this is the Cartesian equation showing the relationship between the y displacement and the x displacement. And if you plot the whole thing, you will actually end up with the actual trajectory of the object. So here is basically the unresisted projectile motion. Now let's have a look at resisted projectile motion. Let's first look at the horizontal component. It is exactly the same as horizontal resist motion we did previously, so really nothing challenging here. As you can see here, acceleration is negatively proportional to the velocity. So we know the velocity will have to be a exponential function. So x dot will equal to a e to the power of negative kt. Yeah. Of course, when you find out what a is, so when t is 0, x dot equals to x naught dot, so the initial velocity. And then that means x dot is just x naught dot e minus kt. Yep. As you can see, the key difference here to unresisted motion is in unresisted motion, the horizontal velocity is just the initial horizontal velocity. Nothing changes. But here, as you can see here, as t increases, e to the power of negative kt will get smaller and smaller. So that means here the x dot, the horizontal velocity, is actually ever diminishing quantity. So that's the idea of resistance, really. The further you go, the more you slow down. All right, to find what the displacement should be, we will have to integrate this. So we end up with this should be no dot. So x should equal to negative x dot naught over k e minus kt plus c. So what is c? Obviously, when t equals to 0, x equals to the initial position. Yeah. So we end up with x naught equals to minus x dot naught over k plus c. So obviously, c equals to x naught plus over k. And if we combine everything together, we end up with x equals to negative x naught dot over k, or x dot naught. Okay, so minus kt plus x naught over k. X dot naught over k plus x naught. Obviously, once again, in most cases you see in this course, the initial displacement will just be taken as 0, and you just end up with x equals to, we can factor x dot naught over k times 1 minus e to the power of negative kt. Okay, so this is our common expression for the displacement. So what we have our acceleration, we have our acceleration, we have our velocity, and we have our displacement. All right, so it should be this one. Yeah, so that's the 3 equations of motion we have for the horizontal direction. Okay, now let's have a look at the vertical direction. So vertical direction is slightly more complicated because we do have gravity in play as well, but it's still the same. The only difference as what we did previously in vertical resistant motion is we no longer have 2 separate systems for up and downwards. Yeah? So both up and down are grouped into a single expression. So the idea is now upward is positive at all times. So G is always downwards. Whether this resistance is up or down depends on the direction of y dot. So if the velocity is going up, this force here, acceleration, is downwards because it's negative. But once the direction of direction of velocity, so once it's coming down, y dot becomes negative. This whole thing becomes positive to indicate the force is now going upwards. So this is the only difference, really. Now, we did write, I'm pretty sure we did, we did write it as equals negative g, g plus ky dot. So this was the differential equation we tried to solve, and solve it we did. We figured out that t would be equal to 1 over k log over g plus k. I'm not going to go through the whole process because we've already done it multiple times. G plus ky dot. Yeah. So this is what we have, and we rearrange everything to make y dot the subject. We end up with g plus ky dot naught over k times e to the power of negative kt minus g over k. Okay, so this is what we have. And we have our acceleration, we have our velocity. Now we need to get displacement. So displacement, we integrate the velocity with respect to time. Yeah, so velocity times time gives us a displacement. So we end up with y equals to divide by negative k, so negative g plus ky dot naught over k squared times e minus kt minus g over kt, and then plus c. Once again, we need to find out c by having t equals to 0 and the y equals to the initial y position. Once again, y position today, it's often the case it's not 0 just because it's not fired from like sea level, well, whatever, bottom level. Okay, yeah, if we work this out, we'll see that this portion disappears, so e disappears, and then we can write as y naught equals to negative g plus ky dot naught over k squared plus c. Okay, so obviously c equals to y naught plus g plus ky dot naught over k squared. Okay, so combine everything. We can just say y equals to negative g plus ky dot naught over a k squared e minus kt minus g over kt plus g plus ky dot naught over k squared plus the original y naught. So as you can see here, this is no longer a parabolic expression like in the unresisted. So it's things are slightly more complicated because once let's simplify this a bit. So y equals to, obviously we can move this to the front, so we end up with and then factor everything else. So it's 1 minus e to the power negative kt times g plus ky dot naught over k squared minus g over kt plus y naught. Okay. The tricky part, as you can see here, it's no longer a quadratic expression, which means it's not that easy to find the time of flight now. Because if you recall previously, for this one, we can easily solve this quadratic equation for y equals to 0 and then get a time of flight. But here, it's not that easy now. But if you really want, what you can do is still to plot this. So here's one I prepared earlier. As you can see here, the expression is the same, but all I did was I used the origin as the level starting point, so I didn't include the initial height. So here, as you can see, we can plot this by varying the k value and the initial velocity, so the proportionality constant for resistance. So by varying it, so as you can see here, the greater resistance, the lower the height will reach, yeah. And then so the quicker it comes down, and then smaller resistance. As you can see, when resistance is really low, it's almost a perfect parabola. But when it's high, it starts tilt, so on. Yeah. Of course, if you increase the velocity, increase initial velocity, it will reach a high height. Yep. So do you remember this is the height and this is time. Now, unfortunately, because there is no equation, we cannot solve this algebraically because we have a t in the position of exponent and a t, a linear term. So we can't really solve it, which means you're given a specific k and your initial velocity. You'll probably have to plot it and read out where this x-intercept is, and this would give you the time of flight. Of course, there's also a slightly different way, which we're going to cover in one of the examples, but that's the nature of this type of questions, where you cannot like obtain a time of flight algebraically, which means if you want to find the horizontal range, because horizontal range depends on the time of flight, then you will also have to basically work it either graphically or trial and error, maybe, possibly, probably not. Okay, now, so for Cartesian equation, it's gonna be a huge beast. So what we have to do is, obviously, this is our horizontal equation for horizontal motion. So I have to rearrange everything into a the t as an object. So it's kx over x dot naught equals to 1 minus e to the power of kt, and then e to the power of negative kt equals to 1 minus k x over x dot naught, and then what you end up with is t equals to negative, so because it becomes log 1 minus kx over x dot naught over k. Okay, and then what you need to do is you substitute its expression into what we have as y, 1 minus e negative kt times g plus ky dot naught over k squared minus g over k times t, and then plus y naught. So you substitute into where the t is. Okay, I'm not going to do it here because it's really hugely messy. But once we go into an actual question, because k, x naught, and they are all constant terms, numbers, so they actually it actually becomes much easier if you want to do it, if you're trying to do it with actual numbers, which is what we would be doing with one of the examples. Okay, I'm gonna note with terminal velocity. So once again, as before, terminal velocity is where g is g over k, because we have that's where the velocity resistance generated by velocity cancels out with the gravity. Yep. So as you can see here, from these two expressions, as t gets really big, I'm not going to use approaches infinity because it's not that big. So as t gets bigger, then x dot will approach 0. Yeah, because this number will just becomes more and more close to 0 due to the power approaching 0. Sorry, we are approaching a huge negative number. But here the this one, this portion, though, so the front portion, yeah, will approach 0. So y dot, but will approach negative g over k. Yeah. So that's the terminal velocity. What does that mean? It means as you reach towards, if the time of flight is long enough, then it will come down almost vertically as the horizontal velocity approaches 0 and the vertical velocity approaches a terminal velocity. Now, we can actually look at it in a graph. So obviously, this is a height versus time graph. So the any velocity here will be the gradient. So we can say, so let's use minus 10 over k, yeah, times t. Wait, why is y? T, yeah. So this is the gradient of this line gives us the terminal velocity as it varies according to k, yeah? So if you can see here, the gradient towards the last portion, the final portion, if the resistance is great enough, then you will see that towards the end, if the time flight is long, yeah? If time flight is long, as you can see here, last portion of the trajectory will become more and more parallel to the terminal velocity here, the gradient here. So the gradient, velocity and velocity here, they become more and more similar regardless of what k is. Yeah, so that's the idea. Vertical velocity, as it approaches the end, if the time for flight is long enough, then it will get closer and closer to the theoretical terminal velocity. So that's one of the properties of resisted projectile motion. So as I mentioned earlier, horizontal velocity will approach 0 and the vertical velocity approaches the terminal velocity. Now let's have a look at some examples. Firstly, it's pretty straightforward one. Information, so vertical and horizontal components are given to you already. So it's 15 and 30. Yeah. So that means x dot equals to 15 meters per second and y dot equals to 30 meters per second. So firstly, let's set up the equations of motion. Yep. So the equations of motion will be x double dot would equal to, obviously, it's 1 over 5, so the proportionality is 1 over 5 x dot. And of course, we know that x dot will have to be a to the power of e minus 1 over 5t. Yeah. Of course, when t equals to 0, x equals to 15. So actually, these are the initial values. Yeah. And then x dot will have to be 15e minus 1 over 5t. Yeah. Next one. Now let's find the displacement. Horizontal displacement will be x equals to this will be negative 15 divided by 1/5 is 75 e negative 1/5 t plus c. So in this case, c equals to, well, x equals to 0. So c equals to 75. And we can just write x equals to 75, 1 minus e to the power of negative 1 over 5t. Okay, so this is our equations of motion for the horizontal direction. So acceleration, velocity, and displacement. Now for the vertical direction, So it's a slightly more involved process. So which means I need more space. Okay, so y double dot, of course, equals to negative 10 plus 1 over 5, so g plus almost of 5 y dot. And then if we try to integrate this, so I can factor out negative 1/5 and becomes so 50 plus y dot. So it makes things slightly easier for us. So obviously dt over dy would equal to negative 5 over 50 plus y dot. And then we integrate both sides. T equals to negative 5 log 50 plus y dot plus c. To find out what c is, when t equals to 0, y dot equals to, sorry, this is x dot, y dot equals to 30. So 0 equals to negative 5 log 50 plus y dot plus c. So c has to equal to, oh, sorry, it's 30 here, my bad. Plus 30. So c just equals to 5 log 80. Hey, substitute everything back in. We end up with t equals to negative 5 log 50 plus y dot plus 5 log 80. Of course, we can just move everything to the one side. So we have negative 1/5 of t equals to log 50 plus y dot divided by 80, because we factor negative 1. We multiply both sides by negative 1/5, so the sign reversed, and then e to the power of negative 1/5 of t equals to 50 plus y dot over 80, which means y dot equals to equals to 80 e negative 1/5 of t plus, sorry, minus 50. Yep. So we have our acceleration, we have our velocity. Now we get displacement. So y equals to, obviously, we integrate this with respect to time. That gives negative 400 e to the power of negative 5t minus 50t, and then plus some, and then plus c. So to find out what c is, we recognize that y initial equals to 0 as well at t equals to 0. So 0 equals to negative 400. Yeah, plus c, so c equals to 400, which means we can simplify everything back down to 400 times 1 minus e negative 1/5t minus 50t. So this is our expression for the For the vertical displacement. Now, what we can do is we can combine the x and the y together to get a Cartesian equation. As you can see here, because we have all numbers here, so things are much more straightforward than all the with all the g and the k and y dot naught we have to deal with earlier. Yeah. So, excuse me. So we have. So firstly, we have to convert t into something about in terms of x. So x equals to 75, 1 minus e to the power of negative 1/5 t. All right, so we need to make t the subject here, which means 1 minus x over 75, so divided by 1 minus equals to e negative 1/5 t. And then we take the log of both sides, so negative 1/5 of t equals to log 1 minus x over 75, and then t is just negative 5 log 1 minus x over 75. So we substitute all of this into y equals to 400 1 minus e negative 1/5 of t minus 50 t. So it becomes y equals to 400 1 minus e negative 1/5 times negative 5 log 1 minus x over 75 minus 50 times negative 5 log 1 minus x over 75. Yeah, so we end up with negative 1/5 cancels out with negative 5, e and log cancels out, so we end up with y equals to 400 times 1 minus x over 75 minus, plus 250 log 1 minus x over 75, and then we end up with y equals to 400x over 75 plus 250 log 1 minus x over 75. And that is our answer. So that's the Cartesian equation, sorry. So as you can see here, we start off with the horizontal acceleration, integrate to find the horizontal velocity, integrate again to find horizontal displacement. Similarly, we solve the differential equation to get the differential equation of the acceleration to get our velocity, and then we integrate velocity again to get our displacement, and then we combine two with a Cartesian equation, and if you plot this, you will actually end up with a trajectory of the object. So let's do that. So it's 400x divided by 75. Plus 250 log 1 minus x divided by 75. Yeah, and then of course we need to zoom out. So here is the trajectory. As you can clearly see, rises and rises, but by the time it reaches height, it will start to slow down, so it will not travel as far. And then the horizontal velocity will decrease quite significantly due to the air resistance. Yeah, but vertical velocity will not decrease as much because it is assisted by the gravity. So you end up with this kind of path here. So this is very typical of resisted projectile motion. Okay, next one. So this one, we have a projectile phi at an angle of 60 degrees, a velocity of 10 root 3 meters per second, where the proportional constant is 0.4. Okay, so that's before we start, let's get the x and the y components of a velocity. Yeah, so obviously v naught equals to 10 root 3, and then x dot naught is 10 root 3, so it should be like this. Yep, so this is v, this is y dot, and then this is x dot. So x equals 10 root 3. Obviously here is cosine 60, which means x naught is equal to 5 root 3. And then we'll do the same for y dot naught equals to 10 root 3. Sine 60, which means y dot equals to 15. Okay, so here are our horizontal and vertical values. Now, firstly, before we actually attempt any of these, we really should figure out set up the equations of motion. So obviously, x dot equals to negative 0.4x, yeah, horizontal resist motion, proportional to the velocity. And solving this equation, we end up with x equals to a e to the power of negative 0.4 t. And of course, a is just the initial velocity. So x dot equals to 5 root 3 negative 0.4 t. Yeah, and then we integrate it again to find the displacement, which is it's 5 divided by 0.4, yet it's negative 12.5 root 3 e negative 0.4 t plus c. So when t is 0, x is 0, so c has to equal to 12.5 root 3. I think you can see a pattern now. So x should be 12.5 root 3 1 minus e to the power of negative 0.4 t. Yep. So this is the horizontal component. Vertical component. Sorry. Wait. Y double dot should equal to obviously negative 10 plus 0.4 y dot. Yep. So gravity plus resistance. So to solve this, we say, well, dy dot dt should equal to negative, actually, yeah, equal to negative 10 plus 0.4 y dot. Okay, so dt over dy dot should equal to, we might as well factor 0.4 out. It probably makes things easier. So negative 1 over 0.4, 25 plus y dot. Okay, so we integrate this, we end up with negative 0.4 t equals to, so I'm just going to move 0.4 t to the other side. equals to log 25 plus y. See, I'm not going to write everything out in detail because we have done this multiple times, but if you want, you can try to write everything out yourself. Yeah. So when t equals to 0, this part disappears. So y dot equals to 15. Yeah, that's our initial velocity. So that means c is negative log 40. Okay, so if we arrange everything together, we will end up with negative 0.4 t equals to log 25 plus y over 40. And of course, we raise both sides to the power of e, and we end up with, this y dot. We end up with y dot equals to 40 e to the power of negative 0.4 t plus, it should be minus 25. Okay, so we have, this is our expression for the vertical velocity, and from there we can work out the displacement by integrating it. So y equals to so negative 100 e to the power of negative 0.4 t minus 25 t plus c. So what is c? When t equals to 0, y equals to 0 as well. So this part disappears, which means c equals to 100. Yeah, so once again, we can just take 100 out, equals to 100. 1 minus e to the power of negative 0.4 t minus 25 t. Okay, so this is our vertical displacement. So we have all our six equations now. So we have acceleration, we have our velocity, we have a horizontal displacement, so we have vertical acceleration, vertical velocity, and the vertical displacement. So in this question, of course, not all of them are used, but generally speaking, it's good to set all of them up so you know what they are. Okay, so next one, maximum height. So obviously, maximum height occurs at when at maximum height, obviously y dot equals to 0. There's no longer any velocity going upwards, so we can just replace it in our velocity equation. So 0 equals to 40 e to the power of 0.4 t minus 25. So to solve this, so e negative 0.4 t would equal to 25 over 40. So t would equal to log 25 over 40 divided by 0.4. Oh, sorry, negative 0.4. So that means t is approximately 1.175 seconds. Okay, next one, the time to the next one should have been the time that max height is reached. So the first one is the time. The second one is the actual height. So for the actual height, we have to substitute this t value into the height equation. So y equals to 100, 1 minus e negative 0.4 times 1.175. Yeah, and then minus 25 times 1.175. All right, so if you punch all of this into a calculator, you end up with y approximately 8125 meters. Yeah, so that's how you find the maximum height and sorry, the time reaches maximum height and the maximum height itself. Okay, so next one, it's trickier. Find when the projectile hits the ground. So one way, of course, we can do it is we can plot the the vertical displacement and find where it hits ground, or we can also use the fact that y equals to 0, so 0 equals to 100, 1 minus e negative 0.4t minus 25t. As I mentioned earlier, you can see that you can't really solve this equation, so we have to use some other approaches. Okay, so because logarithm unfortunately is not an algebraic operation, so you cannot undo it in the form of equation here. Okay, so what do we have? What we end up with is we can just write it as 100, 1 minus e to the power of negative 0.4t equals to 25t. As you can see here, we actually have two expressions. We can have a y equals to 100 times 1 minus e negative 2 power of negative 0.4t, and a y equals to 25t. So what we have is we have two lines, sorry, a curve and a straight line, and we can find where they intersect, because their intersection will provide us with a t value that works for both of them. So what's that? Of course, we can just punch them in. So y equals to 100 times 1 minus e to the power of negative 0.4x. Yep. And then we can also have y equals to 25t. So 25x, sorry, because this is the x-axis. All right. That gives us two lines where they intersect. It's not very helpful. So what I'm going to do is I'm just going to change the ratio of x and y axis. As you can see here, there is a very clear intersection between this. So the value here should be 2.57. Well, unfortunately, GeoGebra rounds off quite many decimal places. But as you can see here, 2.57 is where they intersect, which means t should be approximately 2.57. Cool, isn't it? Now, to find the maximum range, that's the time of flight to, that's the distance flown to 2.57 years, isn't it? So we have our horizontal displacement. So we just have to plug this in, this time into it. So we have x equals to 12.5 root 3 times 1 minus e to the power of negative 0.4 times 2.57. Yeah, if we punch all of this into the calculator, we end up with the x equals to approximately 13.9 meters. And so there is that.